Hello everyone and welcome to the channel. In this video, we'll rework the address decoding circuit we have built in episode 13 and we'll implement it on a breadboard. I hope you enjoy. Okay, so I'm here in digital. In episode 13, we have built this address decoding circuit. So if you haven't seen that episode yet, I would highly recommend you start by watching episode 13 because I'm not going to re-explain what's going on here and I'm going to start making modifications to it right away. So go and watch it and then come back to this video. So I want to do some reworking of this circuit. The main reason why is I'm using here an HC4078, which is an obsolete chip. You can't buy it new. And so I'm trying to build a circuit that you guys can reproduce at home. And so it would be nice if I would only use in production chips. So I'm going to try and rework this circuit so that this chip is not in use anymore. And we'll see how it goes. One thing I want to point out is I forgot something when I was talking about the maximum frequency. And that is we have the 65C22. But we also have the 65C51. And if you look at the 65C51, it's the asynchronous communications interface adapter. So the UART, there is a timing diagram. And it says here that the chip selects need to be ready before the clock goes high at TACW. And so in the table down here, you don't have TACW, you have TAC. I think that's a typo, but it's the address setup time and it's a minimum of 30 nanoseconds at 4 megahertz. So the IO chip select needs to happen 10 nanoseconds before the rising edge of the clock for the 65C22, but it needs to happen 30 nanoseconds for the 51. And so that's going to change our maximum frequency. So this is going to be 78.5 plus 30, which is 108.5, which means that the period of the clock needs to be greater than 217, which means that the maximum frequency is 4.6 megahertz, just for the I/O. And then we have also seen the timing diagram of the ROM. And for the ROM, the period of the clock needs to be greater than 76.5. That's the propagation delay of the I/O pin, plus 19 nanoseconds. That's the time where you need to present data to the buffer for it to be read to the CPU, plus 150 nanoseconds. That's the access time of the ROM. And so that's going to be 245.5 nanoseconds. And so the maximum frequency is going to be 4 megahertz. So as I work on this circuit, I'm going to try and keep it so that the maximum frequency we can attain is 4 megahertz, which is my goal for this computer. Okay, and so just a reminder from episode 13, we have a test case here that runs through all the possibilities of address pins and verifies that the output signals are correct. So as I make modifications to this circuit, I'm going to be able to run the tests to verify that we haven't broken anything. And the tests pass now before I start. First thing I'm going to do is give myself some space here. There we go. All right, so the way that we can replace this chip is by using De Morgan's law. And what that means is we need to invert the output and inputs and change the gate from an OR to an AND. So let me do that now. So this should still work. Yes. And so it would be nice to be able to use the HC30. So if I make this an AND, I can take this and I need to add an inverter at the output. There we go. So of course, this is way worse than when we started. We need to use 9 inverters in order to be able to use this chip, but I'm going to try to reduce this number. So the first thing I'm going to do is replace the 74AC573 we're currently using. It's the Auxhole transparent latch that is latching the bank address in the beginning of the clock cycle. And I'm going to replace it a 74AC563, which is exactly the same chip, but it has inverted outputs. And if you compare the timings of the 74AC573 to the 74AC563, you can see that they're almost identical. And the 563 is even just a bit faster in some places. So we can replace this in our circuit without problem with our timings. What this is going to give us is it's going to invert all of the pins A16 to A23 for us. And so I'm able to replace all those inverters and put them here. And so I'm not changing the values of the pins, I'm just adding inverters here, but just remember these are part of the same chip. So I'm not adding individual inverters here. There you go. And then because the pins are inverted here, I also need to use de Morgan's law to replace this gate. This is what we need in order for the tests to pass. Tests are passing, and so we can use de Morgan's law to replace these inverters and this gate by an AND gate. There we go. Tests are still passing. And so this works. And so this is only using in production chips. What would be nice is to be able to remove this inverter here in order to simplify the circuits even more. And so if we think about it, we can also use de Morgan's law on these gates. So if I replace this with an OR gate, I need to invert the other pin. But we already have it inverted here, so let me change that. Okay, I need to do the same here. This one needs to be 3 inputs, and then this one needs to be inverted, so we can just take it from the main A15. And then this one needs to be inverted. Why did I forget? Oh, this one as well needs to be inverted. There you go. So the AC138 already has inverted inputs. So it would be nice if we could move this line to one of the inverted inputs. And we can do that by switching the bank 0 signal with the A15 here because we are inverting it here. So let me do that now. So I'm going to move this line and this line and invert them. And this is going to be like this. There we go. This is still working. Okay, so I think we can do the same here. Replace the NAND gate with a NOR gate using de Morgan's law. As well, this needs to be a 3-input OR gate as well. Then we can remove this inverter. And we just have to replace those gates with NAND gates. There we go. And the tests are still passing. Okay, so we have a single NOR here that we use for an inverter. But now we have NAND gates that we need. So I'm going to replace the NOR with a NAND to do the inversion. And we just need to change this to 1. And then this inverter we can also make an AND. Okay. So one issue that I'm seeing is we need those 3 inputs OR gates. And we don't actually have a 3-input OR gate that is fast. So it would be nice if those were 2 inputs. And the way to do that is just to chain them. I guess that's the naive version. Okay, so now we have only chips that we can buy and also only chips that are fast. Let me see if I can optimize this further. I think we can again use de Morgan's law here. We have this signal that is inverted and this signal that we can invert. And then we can replace this with an AND gate. So let me do that now. There we go. And I think this could work. So if I count my chips, I have 1, 2, 3, 4 2 input OR gates. So that's a single package. I have 1, 2, 3, 4 NAND gates. That's also a single package. And then I have the HC30 here and the other HC30 here, and then an AC138. So I have 0 wasted gates, only in production chips, and also chips that I can get in a fast variant. So I think that's pretty good. Let me fast forward computing the propagation delays of this circuit, and then we'll talk about it. Okay, so there you have it, the new address decoding circuit. So I'm pretty happy with this result because the new circuit doesn't change the maximum frequency. We still have the same orders of magnitude in propagation delays for the ROM and I/O range, which are both our limiting factors. And our maximum frequency now is 4.08 megahertz, which is still within what I was trying to achieve. The limiting factor in the frequency is the HC30 here and the latching of the bank address. And if I was to replace this chip, for example, with the 74HCT11030 8-input NAND, which has a propagation delay of 8.7 nanoseconds, I would split this up and then the maximum frequency wouldn't change very much. It would be 4.3 megahertz, which isn't a lot. So my point is, if we wanted to go much faster than this, say 6 or 8 megahertz, we would have to do some major refactoring and probably move to a CPLD. As far as address decoding goes, I think this is pretty good. Let's implement this circuit in KiCad and then we can move to the breadboard and see it working. Okay, so I'm here in KiCad. Let's implement the new address decoding circuit. So the first thing we need to do is to go into the glue logic and replace our 74AC573. And it doesn't look like KiCad has the 563 as a symbol. So let me create it. So the pinout is exactly the same. We just need to rename those pins. And this one is actually called LE per the datasheet. There we go. That's the new symbol. Let's add it. So now, of course, all of these lines are inverted. So let me rename them. So now the bus is also inverted, which means that these are also inverted. But so far, that's the only change that we have to make in order to latch the bank address. So this chip is a drop-in replacement. We just have to keep in mind in the rest of our design that A16 to A23 are inverted. So let me update it here. And so now I need to change this bus here because it's no longer A0 to 23, it's A15 and A16 to 23 inverted. And you can join multiple lists of signals just by enclosing them in braces. And you can see that we can unfold either the uninverted version or the inverted version. So the inversion doesn't show here in the dropdown, but these are the inverted signals. And one thing that we can do is we can take this and we can create an alias. If we go to Tools, Bus Definitions, we can create an alias and call it address. And then we can add this first member and then this second member. And then any bus that is called address will have these members automatically. So we can replace this and just call this address. And now if we go to unfold, we have to do it with braces. Sorry. And now we go to unfold, we can get our signals back. And so this is a bit more readable, I guess. Okay, so we have to change this one. This is also our address bus. And this one. Now we have to update the other sheets because this is not a 0 to 23 anymore either. Then we have to update the debug sheet. This is the address bus, and then here, so these are going to be the inverted signals. Okay, and so in order to display the correct values, we have to invert them again to drive the LEDs. So I could either reverse this LED bar and connect it to VCC here, but maybe sometime I want to reuse the debug board and I'm going to find another solution to not invert the address pins. And so it would be a shame if this would wire this way, because I can just replace this chip with the 74HC540, which has inverting outputs. So let's do that now. So the pinout is exactly the same. So it's a drop-in replacement, but this one has inverting outputs. There we go. And that's our debug module updated. And then the last one is the address decoding. Again, this is going to be address. There we go. And now we can work on implementing our circuit. You've already seen me build this circuit in digital, so I'm going to fast forward building it in KiCad so you don't have to sit through this. Okay, so this is the address decoding circuit finalized. I've implemented exactly the same thing as we had in digital, only I mapped it to physical chips and I added the entirety of the 74AHC138, including the address pins, which we didn't have in digital. Those are just mapped to A6, A5, and A4 to give us 8 I/O devices. And so I'm pretty happy with the choice to invert the bank address pins in our circuit, because this really helped us simplify our address decoding. And when we add the external RAM, we'll discuss what we're going to do with those pins. But most likely we're just going to leave them as is, because the RAM doesn't care if one of its address pins is inverted. It's just going to throw it at the inverted address, and we're going to be able to read and write this location transparently without needing to re-invert those pins. One last thing I want to do is I want to update this part of the debug module. I got a new LED bar that is 10 LEDs, and that has some colors. So we're going to be able to color code our LEDs here. And what I want to do is update the schematic so that we're able to implement it on the breadboard afterwards. So let me do that now. So the first thing we can do is replace this 74HC541 with the same chip we use for the inverted bank address. And then we can flip the LED bar and connect it to ground. Then KiCad doesn't have a symbol for the LED bar I'm using. I want to specify the colors here, so I'm going to create a new symbol. Okay, so let's add our new bar to the schematic. I'm going to replace this one. And the way I'm going to hook it up, I've already ordered the signals the right way. The read-write is going to be the blue LED. Then I'm going to have here the emulation LED, which we're going to be able to remove here. And then VDA is going to be green, VPA is going to be green, and RAQ is also going to be green, because these are signals that are normally triggered. So green is good. Then ready, bus enable, and NMI, I'm going to make in yellow, because if these are triggered, then most likely it's working, but it's still something that we should pay attention to. It's more rare to have these signals triggered. And then the wait LED is going to be red, because this is an error condition. And then the last red LED, I'm going to make the reset pin. There we go. In terms of resistors, each color is going to have its own value of resistor. And I've determined that for blue, it's 1.5K. For yellow, it's 1K. For green, it's 3.3K. And red, I can't remember right now. I'll look it up. But we're going to need individual resistors here. For red, it's 1.5K as well. And then these are all going to ground. There we go. So now we need to buffer the emulation LED, which I didn't do before. And the reset pin, we need to add it here. And we have an active low reset. And so it needs to be inverted and buffered. There we go. So this is the new debug module. One last thing I want to change is ready here. I'm only interested in what I'm inputting. So when the CPU is waiting, it's pulling its line low, but we already have this information on the wait LED. So I want to display only ready in. So let me update that. Okay, so this is everything. So we only need to import the remaining pins on the address decoding sheet. There we go. So this is all our updates for KiCad. Let's go into the breadboard and implement the new address decoding circuit and the modifications to the debug circuit. Okay, so this is our breadboard where we left off the last time. As you can see, it's still executing our memory test program. First thing I'm going to do is I'm going to replace the latching chip with a 563. So let me do that now. So I have to remember that it's plugged in the other way around. There we go. So this should still be working. And the bank address is now inverted here. So I have to make the updates to the debug module. So in a previous video, I replaced all those 245 chips with 541, and I didn't do it on a breadboard. So I'm going to have to replace those three as well. And then this one and this one we replace with 540. So let me do that now. And then let's also replace these with 540. Okay, so the only difference between those chips is pin 1 used to be connected to VCC, and now it needs to be connected to ground. So let me do that now. Okay, and now these pull-ups need to be connected to VCC, but I don't have a VCC line here, so I'm going to move them next to the CPU. And then we can keep the pull down on the bank address because the polarity needs to change. So I didn't change it when I was updating schematic. I'll fix this later. Okay, so this should still work. When I need to reverse the polarity of this LED here and add the new one. Okay, this looks like it was working. Let me just check the polarity of my pull-ups by disabling the bus. Yes, so the address is all ones. And this shouldn't be driven now, because I taken bus enable low. Oh, I think what's happening here is, since my read pulse is not linked to bus enable, the ROM is still outputting here. So we need to fix that in the next episode, but the rest of the circuit seems to be working fine. There you go. So now we have proper colors here. And we can move on to implementing the address decoding. So let me remove this temporary circuit that I made here. There we go. So I forgot about the emulation and reset LEDs here. So let me do that now. There we go. So that's emulation and then reset. There we go. Now when I reset, there's a red LED here, and then the emulation LED is turned on, and then wait. Now what I'm going to do is I'm going to work on implementing this circuit here. There we go. So these are all the chips we're going to need. I'm using HCT chips for now because that's what I have in stock, and we'll see about upgrading these later. So they all need power and ground and decoupling capacitors. There we go. Now we have to connect everything up. Okay, so this is all the bank address pins connected to the HCT30. Now let me do the other HCT30. There you go. This is the other HC30. Now let me wire up A15. Then I'm going to wire A23 to A20 to the NAND gate. There you go. Then we need A19 to the OR gate. And finally, for the address pins, we need A4, 5, and 6 connected to the 138. There we go. So these are all the address pins connected. Now let's connect the rest of the gates. So this one is going to be the external RAM. This is going to be the chip select for the RAM. This one is going to be the chip select for the RAM. Okay, so this is all the pins here connected. So we have our 3 chip selects here, and then the 74138 to do the I/O decoding. So let me just replace these with wires. Okay, this should be everything. So now our program should still work. Let me turn on the power and clock it. And it doesn't seem to be working. That's because we have latched here value. So let me just disable the latch chip here by tying its up enable to ground. No, to VCC, sorry. There we go. And then we need to pull down the output value. Oh, sorry, we need to pull up the output value. Let me do that here. There we go. The reason I disabled this chip is because it's an HCT version and I think it's not fast enough, but I don't have an AC version in stock, so we'll have to wait for that. So I disable the bank address so that the HCT30 here returns the correct signal. So let's try again. Let me reset. FFC, FFFD, this looks to be working. And yeah, this is working. And one question I got asked in the last video was, in 16-bit mode, is the CPU actually writing twice to the data bus? So for the low byte and the high byte, and you can see it here. You can see it's writing with the blue LED. I pulse it once to write the first byte, and then it's still writing, and then it gets the second byte. So there is 2 consecutive clock cycles where the CPU is writing in 16-bit mode. Okay, so let me run this program. And it seems that we have an error with the RAM. Let me add a LED on the chip select to make sure that it's activating correctly. And on the ROM as well, even though I think this one is correct. Okay, so let's reset. So now we're reading from the ROM, FFFC and FFFD. This is all from the ROM. It's loading all the instructions. And then we should be writing to the RAM, but this is not turning on, so there's a problem with this signal here. Let me check my schematic. Okay, I figured it out. So the program is writing to the I/O range here, so this is not going to work. So we have to update the program. Let's do that now. Okay, so this is our program that we're currently running. We are testing the RAM. The only issue is we are starting in the I/O range here, and this worked the last time because we didn't decode the I/O range, but now we do. So we have to update this value to the correct end of RAM according to our memory map, which I'll put on the screen. And let me just add a comment. So now this should be working. So let's try the new program. So it looks like it's working. It's writing to addresses that are not in the I/O range. Let's try and speed this up. And it worked. Awesome. So in this video, we've connected the final address decoding circuit that we reworked in digital. And we also made some updates to the debug module. And we were able to verify that the new address decoding works by running our memory test program. So in the next video, I'm going to fix the issue we had with the latch. I'm going to replace it with the correct family. And I'm going to go through all the chips and order the right families, because I think we're now getting into the territory of the timing being critical for working CPU. So I can't just use whatever chip I have in stock. So I'll go ahead and replace all of this. And then we'll work on the read and write pulses. And we'll make them work with bus enable, ready, and we'll talk about VDA and VPA as well. So I hope you enjoyed this one. Let me know in the comments if you've got any questions or feedback. And I hope to see you in the next one. Goodbye.